Okay, our next speaker is Edwin Go from Dr. Seitzman's group, and he's going to be speaking about reduced order models for prediction of stage combustor NOx emissions.
Thank you. So I changed my title from when I submitted it to Dan. I changed it last night. So I'm going to talk about something that's, I guess, less abstract and more practical and more concrete. And I hope that this is the simplest talk you hear today. So I'm going to talk about, like it says up there, finite rate entrainment effects for emissions prediction in stage combustors. And so I have two pictures here, one from Mitsubishi Heavy Industries and one from Siemens. So these two plots that they gave in their respective technical reports show the trend in the gas turbine industry. Essentially, the trend is that as we head towards higher turbine inlet temperatures, we've been getting higher and higher efficiencies. So this has taken a couple decades, maybe 3 decades to get to. And the second plot shows that as we do that, however, emissions becomes an issue because NOx is exponentially dependent on firing temperature. So I think this is Siemens' current state-of-the-art premix combustor that they use right now, lean premix we call it. And we can see that, this is around 80, which is, I think, current regulations are single-digit levels. So really we want to be down here. And this black line here is going to come in later. This is important because this is sort of the best you can do with current technologies. So if you extrapolate this up here, we want to really be here on the right in terms of flame temperature, but we also really want to be here in terms of emissions. So essentially we're trying to push this curve to the right and to the bottom. And how people are looking to do that in industry right now is through stage combustor systems. So this is a patent that I took from Siemens, and this is the traditional combustor that we currently use in most of our power generation plants. So essentially you have fuel and air pre-mixed here and then burns here. This green part I highlighted is a transition piece that directs the hot gases into the turbine. And what stage combustion systems do is they take this green region, shorten it, and then add this yellow region I highlighted here, where they further add fuel and air inside to further increase the temperature. So essentially why this is I'll talk about why this helps with NOx emissions in a little bit. But in addition to Siemens, GE is also looking at this. And I really like this slide because it really shows what's important in the gas turbine industry, what's important for these OEMs, what's important for utilities like Georgia Power. So they really care about emissions because, there are laws, and I think the lower your emissions, it has to do with economy also. So emissions is one thing, but the other thing, especially with all the renewables coming out, is operability, right? You have more factors into your energy mix, like solar, wind. And so when you have those contributing to your electricity, you want the ability to turn down your gas turbines to part load. And so this is, which one is it? Here, load range expansion. And that's also an important consideration. So GE essentially also has a stage combustor. AFS stands for axial fuel staged. And essentially it looks the same. I don't know how the patents differ there, but it's essentially the same concept. You take a simple pre-mixed combustion system and then tag on a secondary stage here. So going back to Siemens results that we saw just now, this black line here is the best that you can do for conventional architectures. And the question then for us when we did this project was, what about AFS, right? What's the best you can do with AFS? So the key assumptions that we had and we could make were, number one, you would maintain this ideal premixing for the main burner, keep this part, but then for the second stage, the ideal case would be for the fuel and air that you inject in that yellow region, if you remember, to mix perfectly with whatever comes out from the main burner before any reactions happen. So these are the key assumptions that we have. And then using these key assumptions, I created a reactor model for an ideal stage combustor. And then I think I have it here. Right, oh, yeah. So going back to this, you have ideal premixing here in this green region, the premixer. And then the second assumption comes in here where you have ideal mixing between gas from here and gas coming in here before reactions. Going back to the model, this is the model I created. That's the ideal one, main burner products, secondary fluid, a mixer that mixes the fluids perfectly before any further reactions occur. So in terms of what reactor I use here, this is a simple closed reactor that's perfectly mixed inside, and that's homogeneous, constant pressure, adiabatic, and all that. So very ideal case. Feed that into an optimization routine, and you figure out that you have to deal with some constraints there. You have to come up with different ranges for parameters, and we got something that looks like this. So essentially, this red line here was that black premix, ideally premixed line that we saw in the Siemens plot. And this blue line is what I found. That's the theoretical limit for an axial fuel stage combustor. So looks really good, right? Essentially, across the board of all our firing temperatures, we can do, theoretically, about a ppm level NOx. And also you have higher improvement as you go to higher firing temperatures, which is good because that's where we're trying to head. Remember the curve, trying to push it to the bottom right. So what we found also from this study is that how you get to this blue curve is to have that yellow section for the secondary burner as short as possible, and also have the main burner run as lean as possible. So really how this ties back into the physics of NOx emissions is that NOx in these systems is governed by a mechanism called thermal NOx, and this mechanism is very dependent on the temperature and residence time. So this made sense to us because it's really saying you want to reduce the temperature at which it's hot and reduce the time at which the temperature is high. So essentially, time and temperature are going to be key aspects going forward as I go through my talk again. Now, why is this result important though? So one thing that the one contribution, I guess, for this set of results is that if a company like Siemens or GE is trying to design a new gas turbine combustor, and they realize they do some experiments and they're up here. So with this set of results, they would know the best you can do is this. So you should be putting more effort, I guess, into pushing your combustor down here. Well, if they're already at, say 5 ppm, then that's probably not such a good investment to bring it down by 4 more ppm. So that's sort of the prior work, the baseline that I'm building up on. And like I said, this is an ideal case. And in real conditions, I guess one question that we had was, how do our assumptions really skew our results, right? What's the worst that we could do? And so practical considerations, I call it. How much do our key mixing assumptions affect NOx and stage combustors? And how I define mixing is we have large-scale entrainment. Okay, so this is when two streams come together, you have turbulence, and those large scales bring the two fluids into close proximity. You have small-scale diffusive-like mixing, which is when the two streams are close together, then those small scales sort of break up the fluid into a homogeneous, locally homogeneous mixture where they can actually react. So each mode, in my case, has a characteristic time associated with it. And I modified that initial reactor model that I had to capture these finite entrainment effects. So, questions? This is kind of the model that I have right now. It's hand-drawn, but essentially what you have is main burner products coming in here, secondary products coming in here, and they go into this, what I call, limited mixing and entrainment region, right? And so the key parameters that I'm going to be talking about, that I'm going to be varying today, are these red ones, tau int main and tau int secondary. So essentially that's, again, this one, right? The characteristic time associated with entrainment. Now you may think, well, this doesn't really look like an actual gas turbine combustor, and so I'll kind of talk through how to look at this model a bit. So this is also hand-drawn, pardon my drawing. This is a typical sort of canonical jet and cross flow picture, right? A lot of us are familiar with it. essentially, one way you could look at this is, see the greens? I color-coded these, right? So the fuel, the secondary fluid is coming through the middle. And then they can go and meet sort of the blue main burner products in this red region. And so this limited mixing and entrainment region is essentially capturing this red interface here in a canonical jet and crossflow problem. So I hope that's clear to everyone. That took me a little while to actually wrap my head around. And so, let's see. Notice how I have this longer. Tau and main is longer than tau and secondary. That's also a key feature because if you think about a jet and crossflow, a lot of this green core material is gone by the time we get up here because a lot of it has reacted. And so sort of typically we would see in a regular jet and crossflow main burner entrainment times that are longer, that take longer to fully entrain into that region than the jet fluid. So another way to look at this is you could view it as sort of this kind of combustor, right, on a bigger scale. So again, color-coded here, blue and green. You would have just a staged entrainment of different fluids into that combustion region. So it really depends on what you want to do with it. But in my case, we're looking more of this problem, kind of. So 2 questions I'm going to answer today. Number 1, how do changing these red parameters affect NOx in a stage combustor, just nominally? Number 2, how does changing this parameter, phi secondary, change NOx in a stage combustor? So let's go into what I did and what I kept fixed. Essentially, we're fixing the exit temperature. 1975 K is the temperature, if you calculate from thermodynamics, that's needed to get to 65% combined cycle efficiency, which means a phi global of around 0.635. I fixed the main burner equivalence ratio to 0.3719. This is a strange number, but it's the optimum main burner equivalence ratio that I found when I was doing the plots for the ideal cases. So this is very lean. I don't think it's very operable in real life. I think instabilities would pop up if you were running this lean. And also we're running a pure fuel jet for now. So secondary, phi secondary is infinity. 25 atmospheres, fuel and air preheat. Well, no preheat on the fuel, 650 preheat for the air. So only thing we're changing is this. And then the NOx results that you see on the right here are for a given main entrainment time, tau and main I call it. And as I vary this tau and sec. So if you look at the picture again, this guy is fixed up here. All I'm changing is this. So you can see the NOx values that I get. Remember we were at 1 ppm before? This is 80 times higher now. So it's a very, very, I guess, big assumption that we're taking off, and it's very important to look at this problem. So the key point to note here is that number 1, let me see if I can go right. I think I have let's see. Okay, not yet. So the key point to note here is that you can potentially have high NOx, but you can also get low NOx. So there's essentially 2 regions, one to the left of this peak and one to the right of this peak. So as you move this guy longer, as the secondary stage takes longer to entrain, essentially once it gets longer than the main burner entrainment, you'll get back to your original NOx levels. And I'll explain why in a bit. So the next slide actually shows So this slide actually shows what's going on, what's going on in the model, right? So we have this picture. This temperature time trace shows what's going on inside the reactor model. Essentially, I think I have arrows. There we go. So over here, you start off here where fuel is entraining. And then in this case, fuel is done entraining here. And then as you keep on entraining main burner products, which are hot, the temperature keeps going up. So somewhere around here probably, you have auto ignition. And this is the key part, this high temperature region. So you have a high temperature region because auto ignition happens close to stoichiometric ratios. And then you have this dilution. before main burner finishes its training. And so essentially what's going on is that it's again a temperature and time issue, right? Over here, why I said this is important, because the final temperature really is 1975 K. Oh no. The final temperature is really 1975 K, but then we're going way above that because of this sort of limited entrainment rate that we're going into the reactor. And so essentially what we have to do is, if we go to, so this is the peak, and here you can see the peak temperature is even higher, right? This is above 24K, 2400, this is below 2400, and also it lasts a lot longer. So this play between temperature and time again shows up here. And then over here you see that there's no temperature overshoot, and that really essentially explains why NOx is low in this case. So I hope that's the sort of the key point. If you don't take anything away, the key thing to note is that in designing these combustion systems, temperature is really the key parameter to reduce emissions. And so 3 general rules that we came up with for this sort of limited entrainment cases. Number 1, if your secondary fluid entrains faster than the main burner fluid, which remember I said is common, right? It's normal. It gives higher NOx than what we had for the infinite rate entrainment. If it's equal, it gives low NOx, because they're always at that final 1975 K and there's no temperature overshoot. If it's slower, then it's good, because you also don't get that overshoot, and it's comparable to the infinite rate. But remember, this is unrealistic, because in a typical jet and crossflow environment, most of your jet will entrain before the main burner is done entraining. So one thing that I looked at to try and sort of work around this limitation is to have premixed secondaries. And this is something Siemens is looking at also, is to divert air into the secondary stage. Remember, I was doing pure fuel only? So we can see that as we add more air into the, I call it jet here, but the secondary stage, essentially we can push the NOx down, again, because temperature is also going down, and we're cutting off some of that overshoot. So there are some parameters that we can play with there, and so we can still achieve low NOx. And so the caveat here is that you end up having a large secondary stage. So when you're at close to stoichiometric jets, your secondary stage is essentially contributing half of the mass of the entire system. So you might end up punching the overall system there. So just a quick summary of what I went through. It was really fast, I'm sorry. NOx can be kept low if we can entrain the secondary stage slower. So this is an engineering challenge. How do we entrain secondary fluid slower than the main burner fluid? Could be some sort of distributed injection system, could be porous walls or things like that. And under more realistic conditions, one approach is to use premixed secondary jets. And so current work is I'm looking for a scaling for NOx position entrainment, something that's easier to comprehend rather than having to look at all the time traces. And why I do this is to allow for better physical understanding. Right? To be honest, a lot of the stuff I showed, anyone could do it with some basic understanding of combustion. So really what is key here is to come up with sort of an analytic expression for NOx to get a better understanding of how the entrainment rates control the temperature, which then control the NOx production. So this analytic model can also be used in a design optimization setting to allow for NOx prediction, because this model is still, it's fast, a lot faster than LES, but it still takes a minute per case. So it's not really tractable in an optimization setting quite yet. And so for a given set of entrainment rates, we'll have to predict these. And essentially what we're predicting is this region, right? This is where all the NOx is produced. So this is the most important part. And also performing optimization studies to come up with the best combination of parameters to give low NOx. Thank you.
Questions?
Yes.
I know it's not directly related to what you're working on, but is there a performance cost to staged combustion since you're going to take an additional pressure drop to push air into the secondary?
So I haven't looked into the pressure issue yet. Everything we've been doing is constant pressure. But yeah, that could be, that's probably a big consideration also, especially when I looked at all the patents. They talked a lot about how they do the routing.
Yeah.
I think that's a big consideration. Simple talk, everyone understood everything?
I guess I'll take Dan's question, but what are some challenges that you face in this setup?
Right, so the main challenge I had in all this was a lot of, so what we just saw here was, I think, 220,000 discrete cases, discrete simulation points. And so it was really hard because I was running on the school's cluster, and this resulted in about 2 terabytes of data. And so data analysis was really hard. Just reading the data into my computer so that I could look at it took about half an hour. And doing anything sort of manipulation on it to calculate the average Knox values, for example, would take an hour. So data processing, I have a workflow now where I'm working in batches. So I load maybe 100 gigs at a time into my laptop or my lab computer. And then once I'm done with it, I delete it and then go through another set of data. So one thing I'm always looking to do still is try how do I compress that data so that it's more friendly to work with. And also another challenge is also always the fact that a lot of this work was done, most of, I think all of it really, was done in Kintera. So figuring out how to tie that API into an optimization algorithm, how to tie that API to do what I wanted to do, which is a stage combustor simulation. That was, I think, a major part of a major learning curve for me, at least. So speaking of that, just to put it out there, I have a repository on GitHub for anyone who wants to use Kintera to do things. I have some really